Welcome this afternoon. Our presentation today is 16 nearly impossible issues for evolutionists to answer. Now, before I begin, I'd like to mention that in July of 1978, in a History of American Education class, I was treated to a lecture which frankly had nothing to do with education, but did have to do with the 4 philosophical schools of thought. And I want you to keep these schools of thought in mind when answering the question, how do we know that anything is true? On what basis do we judge whether something is true or not true? Those schools of thought are absolutism, which means somebody told you; empiricism, which means somebody tested it; pragmatic, which means somebody found out that it worked; existential, which means somebody found out that it occurred. Now, I would propose to you today that the empirical school of thought, number 2, is the most appropriate because we're dealing with issues of science and science only. And how much ever evidence we obtain, we draw our conclusions tentatively and hold them tentatively. We assess them according to a probability of maybe it's high, maybe it's low, maybe it's somewhere in between, but in no case is it 0 or 100%. Because, among other things, nobody can have all the data all the time, everywhere. And even if we did, we might have to filter out noise, contamination, who knows what. And more especially because we don't have all the information available all the time, we need to be open to the possibility that new information will come in. And even if we draw our conclusions again, more information might come in. It's a never-ending process. The 16 issues, therefore: why does anything exist? Without anything, we don't have anything to begin with. We don't even have any people here and so forth. We're going to get into that. Did the universe always exist? And did the universe cause itself to exist? These two questions form a coupled pair with respect to the cosmological argument. How can the universe avoid heat death? Is that even possible? If it isn't, what's going to happen then? How can any material travel faster than the speed of light? You might have thought that no material can, but some people argue to the contrary. What is the origin, transportation, and distribution of carbon? Only the first of these issues has ever really been covered. The other two never have. How do any stars exist, especially if you start with a Big Bang? How do moons form? There's a lot on this subject I'm going to be covering. What is the ongoing source of long-term comets? Short-term comets and long-term comets have different solutions. How do any elements heavier than iron exist? Iron happens to exist in the middle of a particular curve. In fact, it is maximized at on that curve. Why aren't the other elements favored, therefore? How do peptide bonds exist? We have amino acids, we'd like to hook them together, but it's not favored under a warm little pond. What can we do then? The amino acids themselves in proteins are all left-handed. Why should that be when one can get an equal mixture of lefts and right-handeds in a neutral ingredients, neutral environment, neutral energy source situation? What turned non-life into life? Even if I have a dead dog, if I have all the component ingredients, why is it such a Herculean task to go from that point onward? How does metamorphosis occur? There are at least 2 metamorphosis situations. One's with amphibians, and the other is with insects. I'll be dealing with the latter. How do major morphological changes occur, as in going from a fish to an amphibian to a reptile to a bird to a mammal? What creates information from gibberish? If I have letters, numbers scattered about, how can we tell what makes sense and what doesn't? And how can we get these to communicate by chance? Is that even possible? Let me now start with the first. Why does anything exist? It's been said that from nothing, nothing can come. If we don't have anything to begin with, we're not even here. And this is a major challenge. In fact, I would propose that we start with this book, Roget's Pocket Thesaurus. Topic number 1. Would you like to take a guess what it is? Existence. Roget's Pocket Thesaurus is actually not just a treasury of synonyms and antonyms, but in fact, we can study a whole lot about the structure of a language just from this set of synonyms and antonyms. And it stands to reason that if topic number 1 is existence, that the topics in the back might deal with the possible sources of that existence. Now, I'd like to also say something about the universe itself. Not only do we have to deal with the question of why does anything exist, but why this particular amount of material as opposed to some other. It's been estimated that there are approximately 10 to the 80th atoms in the universe. Why not 10 to the 79th? Why not 10 to the 81st? And why have them distributed in the way they've been distributed, whether on the Earth or elsewhere? These are more or less unanswerable because what we would expect by chance is that everything would be scattered out uniformly and it would just stay there that way. That's not the way things actually do exist. How's that? Also, I'd like to mention something about quantum fluctuations. There is a theory these days that says that we could start from nothing and we could get a particle and an antiparticle, and they could come back to nothing if they wish to, but that we could continue to form particles and antiparticles as long as they're matched. Well, what happens if a particle and its antiparticle actually come back together? Do they come back to nothing? No, they don't. In fact, they form energy. The two particles annihilate each other, and energy is formed. So if that scenario were really true, then we could be producing unlimited amounts of energy from nothing. This is a violation of the first law of thermodynamics. Now, let me say something about thermodynamics. There are 3 laws of thermodynamics as illustrated in my graduate physical chemistry textbook in its preface. I had this chemistry class only a few months after the education class that I referred to earlier. The 3 laws of thermodynamics are, 1, that energy mass of the universe is constant, or in darkly humorous form, you can't win, the best you can do is break even. The second law is that entropy is continually increasing, or in darkly humorous form, you can only break even at absolute zero. And the third law speaks for itself, you can't reach absolute zero. There's also a 0th law that says you must play the game. So the ultimate conclusion is you must lose. That's what thermodynamics would have to tell us. And by the way, they haven't handed out any doctoral degrees in thermodynamics ever since the 1940s because the subject is that well known. It's been that well studied. There's really no question as to what it is. It's the best of all subjects in the sciences as far as being studied. So I would propose that the quantum fluctuation scenario that has been given, mostly the public, is not correct. It is not that nothing creates particles which can come back together, but rather that there's an already existing energy field which produces these particles which can come back into the energy field. In fact, that's the actual truth. That's the actual scenario. The public has been led to believe that it's nothing that produces something, but that's not even what those who propose the theory say about the theory. Did the universe always exist? No, because if it did, we wouldn't be here. Everything would have already dissipated according to the second law of thermodynamics, which we already recall says that the entropy of the universe is constantly increasing. Any number of things come to mind at this point, especially the next question, did the universe cause itself to exist? And I've had people answer in the affirmative to the first question, did the universe always exist? And then to be told that it doesn't. Now come to this question, did the universe cause itself to exist? And answer the affirmative to this question, even though answering this question in the affirmative contradicts answering the previous question in the affirmative. Did the universe cause itself to exist? No, because if it did, it would have had to have existed before it existed to cause itself to exist. This is a logical contradiction. With these two questions, did the universe always exist, and did the universe cause itself to exist, I have now ruled out all possible material causes for the universe. Because everything else that might be considered such a cause is a subset of that. So therefore, I have only two possibilities left. Either there is no cause, in which case the person who believes that is an Eastern mystic, the conversation ends because it's outside the field of science, or there still is a cause, but it must be immaterial. Choose from the following possible immaterial causes to the universe. Fairies, leprechauns, gnomes. My favorite, flying spaghetti monster. God, you add to the list. Oh, by the way, only God even has any testimony. So to those who would say that my theory is no better than a flying spaghetti monster, I would answer in return, I don't believe in a flying spaghetti monster. You do. And I never have an argument at that point. How can the universe avoid heat death? According to the laws of thermodynamics, it's not possible to avoid heat death. There are those who would believe that the universe operates according to other laws that have never yet been discovered. I would ask, what are those other laws, and what is the evidence for saying that? In fact, I keep coming back to this same point. How do we know that something's true? Is it true because somebody told you? Is it true because you tested it? Is it true because you found it works? Or is it true because it just happens to occur? Excuse me?
It's true because it's written in the Bible.
I haven't even referred to anything else than science textbooks at this point. And I'm not going to either.
Okay.
All right. I'm just saying that according to the laws of thermodynamics, heat death is unavoidable. Le Chatelier's principle will guarantee that there will be no motivation once the useful energy is no longer useful. There will be nothing to motivate anything, and everything will be experiencing heat death.
We already are.
Number 5. How can any material travel faster than the speed of light? Well, most people would say that isn't even possible. There isn't any. However, those who would involve themselves in the Big Bang have a problem. The problem is trying to account for the ambient noise at 2.7 degrees Kelvin being more or less anisotropic, or in other words, uniform throughout the universe already. How is that possible? The only scenario that's been posited to this point is that at approximately 10 to the minus 31 seconds, the universe hyperinflated, meaning it went much, much, much faster than the speed of light. And only then. Now, I would ask in return, what is the basis for saying that the universe ever behaved this way other than to try to protect one's theory? Well, if the present is really the key to the past, then we should also have experienced other spikes of hyperinflation as well. And yet nobody even proposes that they occurred. So why that one particular spike? And by the way, why at 10 to the minus 31 seconds when we have no instruments that are capable of registering 10 to the minus 31 seconds at all? It's too small a decimal. There aren't any measuring devices that will allow us to tell us why not 10 to the minus 32 or 10 to the minus 30 or some other figure. What is the origin, transportation, and distribution of carbon? Now, I'd like to ask our audience, what does this picture show or not show regarding carbon? What kinds of examples of carbon do we have depicted or not depicted? Well, a diamond is one, right. What's another one that this shows? Right, that lump of coal right there. Okay, what else? How about that green stuff? What would that be? Plant material, right?
Yeah.
Okay. What else does it depict or not depict? How about carbon dioxide, which you can't see? How about carbon monoxide? How about methane? In other words, the gas that you can't see. There are any number of gases that are also. My question isn't with respect to each of those compounds. My question is with respect to how do we get the carbon in the first place? Now, last time I checked, the only explanation from the secular world is that, and this was the object of a Nobel Prize in the 1950s, is that two helium atoms that were fused in the first place from hydrogen on stars came together and formed a transitory molecular weight 8 species, which, by the way, according to this book, will only exist for about 10 to the minus 15 seconds at most. It and atomic weight 5 are not possible to form species, that is, atomic species that will stay around for any length of time. But before, in fact, it could fly apart in that length of time, a third helium atom came to collide with the two that existed to form atomic weight 12. This would be the stable version of carbon. What never gets answered is, under what conditions can that be even possible? It can only occur at one nuclear resonance, only in red giant stars, and can be disseminated only by a supernova. Our sun has never been a red giant star. And even when it reaches the stage where it would be a red giant star, it does not fulfill the conditions required to supernova. Supernova, by the way, only occur, at least our observations, at about once every 50 years. And before our super powerful telescopes, we had only recorded 3 in the first place. That's it. In other words, supernova are extremely rare events too. Where is the nearest red giant star now? It's about 33 light years away from here at a minimum, maybe even 40. Now, how is anything that is 33 to 40 light years away going to be sending us, and more or less us only, all of that carbon when it was flying out in all directions, because that's what a supernova will do? It doesn't just simply jet in one direction. And by the way, even if it were to, how would we expect to see miles deep, thousands of miles long coal beds in several places throughout the Earth? That's solid coal from granular carbon. Talk about dark matter. No, I think there must be some other explanation than that. But let the scientists come up with them. I'm willing to listen. You come up with a good scenario. We'll have our lab coats on. We'll take our measuring devices. We'll sit there as long as it's needed, as long as we're alive to make the measurements and to comment upon them. Whatever it takes. Because that's what empiricism is about. It's being open to the evidence wherever it leads, not where it doesn't lead. Well, why don't we just ask this question instead? How do stars exist? How do any stars exist? If we start off with a Big Bang theory, everything is shooting out in all different directions. According to Newton's laws, what will happen to those particles? They will keep going and going and going and never stop. They'll just keep going. What does it take to form a star? Gravitation of a large expanse of gas. We have trouble collapsing gases even with deliberate devices. How much less in an environment where there is no compression device, which would be what would be required, and for such a volume too. We shouldn't expect to see any stars at all, frankly, let alone the red giant stars that would be required to produce our carbon. How do moons form? Most of the moons in the solar system are around gaseous planets. how do we expect to get a solid moon from a gaseous planet? I don't have any answers to a question like that, frankly. Even if a gaseous planet such as Jupiter, Saturn, Uranus, Neptune, these are our gaseous planets, were to capture material that would be made for a moon, it would have to orbit the moon in just exactly the moon would have to orbit the planet in just such a way as to have the correct shape that we now know exists, and also not break apart according to tidal forces, which would occur if it came too close. This is called Roche's limit. And most of the moons in the solar system are around the gaseous planets. Very few of them are not. But we have a moon too. How could it be formed? The scenario is generally thought to be that something impacted the Earth, caused the material to come out of the Earth far enough away to escape Roche's limit, and voila, we have a moon. Let's examine the actual mechanics. If anything would come into the Earth, the most likely thing is that it would impact the Earth and stay there in the Earth. It wouldn't come out and do anything else. But let's suppose, in fact, that it did eject material. Where? The Pacific Ocean region, maybe? Well, first of all, it can't be blasting the ocean out either, because we would have to account for an ocean moon instead of the solid moon that we have. So we'd have to also posit that there was no ocean there. Very well, no ocean. Pacific region. Blast the Pacific region, material has to come out. Same problem with Roche's limit, which is about 1 to 2% out away from the Earth. If it doesn't get farther than 1 to 2% before it can congeal, it will fall back to the Earth, and there goes our moon. But let's suppose, in fact, that it can go beyond that point. And let's also make the assumption that it has any tangential velocity, because, in fact, if it doesn't have any tangential velocity, it has only two possible paths. Either it keeps going and going, which means that it has reached escape velocity and will never come back to the Earth, save a chance event, or it will fall back to the Earth because it hasn't reached escape velocity. The midway between, the point between them is to have a tangential velocity that will cause it to go in an orbit. It's a very precise thing. If we were to expect it to go straight out from us and achieve a tangential velocity that is in keeping with it, it would have to achieve a geosynchronous orbit versus the actual orbit, which is quite a ways beyond that, and has a period of about 1/28th to 1/30th of a day. 28 to 30 days, so that instead of orbiting the Earth once a day, instead it's orbiting the Earth once a month. Which would you like? None of these is probable, mind you. In fact, the capture theory is regarded so little by evolutionists that almost none of them even believe that that's it. It's too coincidental. It's too close to miraculous for comfort. What is the ongoing source of comets? There are short-term comets, such as Halley's Comet, which are approximately 200 years or less in their orbit. And then there are other comets, which are called the long-term comets. The short-term comets can be generally explained, it's believed, between the interplanetary disk or Kuiper's belt. Not every long-term comet is going to be explained this way. Instead, it's been hypothesized that there is an Oort cloud, spelled O-O-R-T, which is essentially a repository or an automatic pitcher, if you like, of dirty snowballs to sending out comets, conveniently, of course, to account for the ones that get lost in the process of orbiting, such as those that might fall into the sun, those that would lose their mass otherwise. In any event, to try to account for a more or less constant number of comets of that length. Nobody has ever seen the Oort cloud. Nobody has even any actual physical evidence of the Oort cloud. But I'm willing, as an empiricist, to listen to all comers who would come up with evidence for an Oort cloud. Bring me your Oort cloud, and we'll start talking about Oort clouds in actuality and what they would actually do. But until there is actual evidence for an Oort cloud presented according to known scientific laws, not according to laws that we believe will occur in the future, I would suggest that that hypothesis is not better than a flying spaghetti monster. How do any elements heavier than iron exist? In the same year that I took the education class that I mentioned, and that I had the physical chemistry class that I mentioned, earlier that same year, I got this modern physics textbook for a modern physics class that I was taking. And in chapter 9 of this textbook is a graph called the binding energy per nucleon curve. Maximizes out at molecular weight 55, 56, something like that. It's in the region of iron, which means that from a nuclear standpoint, iron is favored above all other elements being formed. How do we get any elements beyond iron? Cobalt, nickel, copper, zinc, all the way up to element 92, uranium. All those elements from cobalt at 27 to uranium at 92, you got to explain how they came about. And I have seen some wonderful explanations. They seem fanciful to me, but not really any mechanisms that have been shown to show the entire table, although I've seen scenarios of how they're produced. In any event, iron is still believed to be at the core of the Earth instead of uranium. How do we account for all that much iron? Well, I would say the binding energy per nucleon curve is pretty good. It's the existence of all those other elements that I would ask. Now, you might be able to start with hydrogen and get all the way to iron. How do you get beyond iron? That's what's never explained. How do peptide bonds exist? I have in my hands depictions of amino acids. I'll get to the matter of left-handed and right-handed later. Let me just take one of these. If you look at this very carefully, you'll see a depiction of NH, actually NH2 for the amine group, CH for the carbon and hydrogen, and an R group for a functional group, and COOH, the carboxylic acid group. This is a depiction of an amino acid. So is the other, namely its mirror image form. To form peptide bonds from this NHCHCO, NHCHCO, and so forth, to chain them, we need to drop a water molecule. This hydroxyl group and this hydrogen are what drop out to form the water molecule that's lost. Have you by any chance heard the theory that we came from a warm little pond? Just how is that going to occur when a water molecule must drop out rather than be absorbed by the amino acid? Something to think about. Now, as regards the question, how do proteins have only L amino acids? L stands for levorotatory, or in other words, left-handed. Let me picture this as being my left-handed one, and this being my right-handed one. If you look at these very carefully, you will see that they are mirror images of each other. This matches for this matches for that, and so forth. However, no matter what one does, as long as one does not break the bonds, it is not possible to superimpose one on top of the other so that they all match. They won't. The best you can do is 2 out of 4. Meaning, the left-handed and right-handed amino acids are actually different molecules. Now, they will have the same melting point, boiling point, refractive index, vapor pressure, density, chemical reactivity, all the same environmental properties. They only differ in one respect. One rotates plane polarized light by a certain amount in one direction, and the other by the same amount in the other direction. In neutral ingredients, neutral environment, neutral energy source, a 50-50 mixture of amino acids is what will form if there are going to be any amino acids. However, in proteins, only the left-handed ones occur. Every single protein in Every amino acid in every protein of every species is only left-handed. There are no right-handed ones. There are right-handed ones in other structures, such as bacterial cell walls. In fact, the bacteria would die if they had left-handed ones, because enzymes, which are composed of nothing but proteins which have left-handed amino acids only, would kill the bacteria. The bacterial cell walls are therefore meant to protect the bacteria from enzymes dissolving them. If bacteria ever encounter a right-handed amino acid, the bacteria will turn the right-handed amino acid into a left-handed amino acid to digest it, if it can digest it. Now, I'd like to point out something about this figure. You'll see the carboxylic acid in orange at the upper corner. You'll see the R group, the functional group, towards the middle of the figure. You'll see the amines groups towards the extremes of the figure, and the hydrogen group at the top. The bond angle of a carbon that has nothing but equal components, as in methane, carbon tetrachloride, and so forth, can be found by taking this cube, which is superimposing the tetrahedron in which this is. There are two tetrahedra, in fact, illustrated by this. They're both embedded in the same cube. If I take the long diagonal, I can determine, because it'll be the square root of 3 times 1 unit, I can determine what the bond angle is going to be. Using geometry, it'll be the arc cosine of minus 1/3, which is approximately 109 degrees, 28 minutes, 16 seconds. It's an exercise that even a high school student should be able to do. I only wish they would teach it in the high schools, because it is possible. I didn't learn about these things until I was a freshman in college, which was a little late.
That's because they teach that creationism. Yeah, that's real helpful.
Oh, well, whatever you might ascribe it to, I didn't find out. And neither did the evolutionists find out about this either. None of us had found out about these things. In any event, we can assess what the actual bond angle is from the R group, or at least the R group is going to be what will determine what the bond angle is. So we can determine, or at least we can discover, which R group we have. One R group will stretch the amino acid in a slightly different direction than another. The R groups themselves, by the way, can consist of either a hydrogen or any of 19 other functional groups, with a total complement of 20 such amino acids possible in living beings such as us. There are actually about 26 if you count everything, I understand. In any event, that's a little bit about left-handed amino acids. I remember seeing a description by Isaac Asimov regarding this matter a number of years ago. And when all was said and done, Isaac Asimov had no other explanation than to say it just happened one way instead of the other. To which, if Isaac Asimov had been here, I would have asked, why only that way across the entire face of the globe? And no, they don't replicate and cause things to spread out. That's just not the way the chemistry works, and he ought to have known better. What turned non-life into life? Suppose I give you a dead dog. Everything's already there. The heart, the brain, the liver, the spleen, the blood vessels, the blood. All in its proper place. I give this to you, Hercules. All you need to do is perform one small task. If this dog is dead, say by a certain amount, 3-4 days, whatever it takes, breathe life into this dog. What's the matter, Hercules? Are you unable to perform this small task I put in front of you? Aren't you Hercules? Well, maybe it's much bigger than that after all. If we can't even breathe life into a dead dog, how do we expect to breathe life into materials constructed into a dead dog? Meaning we have more problems than just getting life into the dog. We also have the problem of getting the dog at all. But even if I give you the dog, breathe life into it. Problem. How does metamorphosis occur? There are at least two kinds. One is from the amphibians, and another is from the insects. Here we have pictured from the insects. I might even be able to grant you an adult butterfly laying eggs. and those eggs rather, hatching into larvae. And for the larvae to go into a cocoon, a pupa. What I have trouble with is, how does the pupa, in its mushy state, without being able to control its own destiny, form the adult? I haven't seen any explanations of this. But you biologists out there, you tell me how you can get the mushy stuff to turn into a butterfly? I'll listen. I've been wanting to know that for quite a while. How do major morphological changes occur? How do we get from an amphibian to a bird? Thank you very much for your time, ma'am. How do we get from feathers to, how do we get scales to feathers? How do we go from cold-blooded to warm-blooded? And how do we get these to exist in going from both in a male and a female to produce a colony? How is that possible? What creates information from gibberish? We have the autocorrelation function whereby we might be able to accurately describe what constitutes information versus gibberish. If I put the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we can see order in these. If I shake them up to come up with, say 1, 8, 5, 2, 7, 3, 4, 6, it would appear as if they would be more random. The autocorrelation function will be able to tell us how random that will be versus the order in the first place. I would like to ask, how in the world can you get that information where it's more ordered from that which is not, which you've shaken things up? We can also extend that to the ambiguity function, whereby we could measure things in several different dimensions. We have much the same problem, though.